Okay, so part 2 of the chapter 13 lecture. So this will be the last video of the course. Okay, so the last video of our last chapter. So as we mentioned in the first part, we had the reinforced algorithm, which was a Monte Carlo algorithm and therefore had a high variability. Okay, so the update rule involved the return, which is the sum of all discounted rewards until the end of the episode. So we have to wait until the end of the episode before making our updates. Okay. Another issue why it's quite volatile and unstable is that in the reinforced algorithm, as we mentioned, every time we take an action in a given state, the reinforced algorithm always increases its probability. So if we have a high return, it's going to increase its probability by a lot. If we have a very low return, it's going to increase a probability, but just by a little bit. So over the long run, actions which are associated with higher returns are increased more than the other ones. And we said why when we increase the probabilities of actions a lot, this must decrease the probability of other actions a lot. So over the long run, you end up increasing the probabilities of good actions. And for bad actions, well, when they're selected, these actions, the probability of such actions are increased, but when other actions are taken, the probability of such actions are decreased. So over the long run, bad actions, the probability for bad actions are decreased, okay, because they are decreased more extensively than the amount in which they're increased when they're selected. Okay. But this might be weird, okay, because when we have a bad action, reinforce says we're going to increase its probability but just by a little bit. Well, we might think that instead of increasing a little bit, why don't we decrease it? Okay, let's consider the following. When we find good actions, we should increase their probability, but when we select bad actions, instead of increasing their probability just a little bit, we should directly decrease them. This is a very valid idea, but if we do that, the problem consists in finding what's a suitable threshold. How do we decide when an action is good, or how do we decide when an action is bad? Well, we probably have to fix some threshold and say if the return falls above this threshold, then it's going to be a good action. If the return falls below that threshold, then it's a bad action and we're going to decrease the probability. Okay, so the problem in that case would be to identify a suitable threshold, which is what we will discuss shortly. Okay, so this threshold we just discussed, we're going to call it a baseline. Okay, so the baseline, which we're going to denote B, is the threshold which determines if the return is above this threshold, we're going to increase the probability of the action selected. If for a given selected action the return falls below that threshold, we're going to decrease the probability of that action. And furthermore, the threshold, it can vary across the various states. Okay, so some states might be associated with very high returns in average. Some states might be associated with very low returns in average. So it makes sense to have the threshold vary across the various states. Okay, so this function B, which where you have a threshold for each state, so it's a function which takes a state and returns a threshold being a real number. This is called the baseline. Okay, so the baseline is the set of thresholds where we have one threshold per state. Okay, one quick thing we notice here if we sum, okay, so this expression, for now it seems weird. Where does it come from? We'll just explain that shortly. But if we consider the following expression, so if we sum all actions over all actions, the baseline evaluated in the state S times the gradient of the probability of selecting action A, given we're in that state S, or and for current values of the parameter, then BS, it doesn't depend on A, so we can put it in front of the summation. We can enter the summation inside the gradient. And here, when we sum the probabilities of selecting the various actions A, it becomes 1, and the gradient of 1 is 0. Okay, so one quick note here, this expression that we're going to use shortly, it's equal to 0. So, what we can do here, we can use what we had as this is the policy gradient theorem. Our policy gradient theorem says that the gradient of the objective function we're trying to maximize is proportional to this quantity. So the sum across all states of the on-policy distribution of the sum across all actions of the action value function times the gradient of the probabilities of selecting action A. Okay, but now we will modify slightly this expression to consider what we had above, because when we sum across all actions, the baseline times the gradient, it's equal to 0. Okay, so here, we instead of Q, we can write Q minus 0, and that 0 here we can substitute by this term here and factor out the gradient. Okay, so this Q minus 0, it becomes Q minus this. Sorry, okay. Maybe I'll write it, it's going to be more clear. Okay, so here, this guy can be minus 0. Okay, whoops. We're gonna do that. This is this minus 0. So instead of having 0, we can take this guy, plug it here, factor out this summation across A and this gradient here. So if we factor out the summation here and the gradient, we obtain that this is, we can instead subtract the action value function by B, and this doesn't change the expression. Okay, so we can take the policy gradient theorem and obtain an alternative representation where instead of having the action value function, we can have the action value function minus the baseline here. And here, the baseline, it can be any function B, which only depends on states, but not on actions. Okay, so their threshold cannot depend on actions. It must only depend on states. And then we have this entire expression here. Okay. So, okay, this may be okay. So here, we won't repeat the steps, but you can go back to what we did earlier in the chapter, do exactly all the same steps, and have that this, okay, maybe I'll outline this. This is an expectation under the current policy of, so here we can multiply by pi and divide by pi here. So if we do that, we can see that this is an expectation of Q. So I won't write the indices, but I'll just have a quick notation here. Nabla pi divided by pi. Okay, so this is what we've done. This is the gradient sign here. So using exactly the same step we had earlier, we can obtain that the gradient will be proportional to the expected value of the action value function minus the baseline times the gradient of pi with respect to pi. Okay, so doing this, we can we can have this, and then this becomes the second line here. Okay, because we in the previous slide we just showed that the gradient is an expectation of the Q function minus the baseline times the gradient of pi with respect to pi. Okay, but recall here that the Q, okay, I'll use very informal notation here, but the action value function is the expected conditional expectation of the return here, given current action and state. Okay, so if we replace Q by this, and here this gradient and this probability, because they're a function of A and S, we can throw them. Okay, so here, okay. Using similar steps, I won't do all the formal math here, but using similar steps, we can show that we can replace the Q by this, and here we can replace B. Okay, so BS is equal to expected value of BS given SA. Okay, so if we condition on S, its conditional expectation is BS itself, because when we condition on S, BS is simply treated as a constant. So we can do that, replace Q and B by these conditional expectations, enter the gradient of the probability and the probability inside the conditional expectations, take double theorem exactly as we did earlier, and then the end result we obtain is just the big large equation here that we obtain. Okay, so here we have the following result, which is the gradient of the objective function we're trying to maximize is proportional to the expectation under the on-policy distribution of the return minus the baseline times the gradient of pi with respect to pi itself. Okay, so the reinforced algorithm we considered earlier used this expression with the specific case b is equal to 0. Okay, so we said b can be any function which depends only on state, so b can be 0, and this would be fine. Okay, so reinforce is basically using a baseline of 0. Okay, so 0 is the threshold. Okay, so here I haven't mentioned that. I said, okay, maybe I'll clarify this. I said earlier that reinforce always increases your probability of selecting an action A, but this is only true if the returns are always positive, because if the return is negative sometimes, then you will decrease its probability. Okay, so I was not exactly accurate. I was exactly accurate if returns are always positive, if rewards are always positive, but if you have negative rewards, for example, it's possible that you decrease the probability of an action, and the threshold in which you decide if you increase or decrease the probability of that action is 0. So if the return is greater than 0, you'll increase the probability of action A. If the return is smaller than 0, then you'll decrease the probability of action A. But in what follows, instead of having a threshold of 0, we're going to say we can consider other thresholds. Okay, so that new threshold in state S will be B of S. So B of S will determine when you're in state S, if the return is higher than B, you will increase it. If the return is lower than B, you will decrease it. Okay, so this is what we're going to see shortly. But first, we have noticed that the gradient of the objective function is proportional to the expectation of this guy. So what we're going to do if we wanted to have a regular gradient ascent, we would need a gradient, which is not computable. But in practice, instead of a regular gradient ascent, we're going to do a stochastic gradient ascent. And instead of the gradient, we're going to use what's inside the expectation, because what's inside is an unbiased estimate of the gradient. Okay, very good. So this entails using the following update rule here, which is that the next parameters is the previous parameters plus the learning rate times this guy here. This is what was inside the expectation. It's the difference between the return and the baseline times the gradient of the probability of action A divided by the probability of the action A. And again, this guy, you can, instead of the gradient of pi over pi, is simply equal to the gradient of log of pi. Okay, so why we express this as the log? It's because, for example, when we had the softmax normalization, sometimes it's more convenient numerically to calculate, because the softmax involves some exponentials, so there are some exponentials that cancel out with the log, and sometimes numerically it's more convenient to calculate the log than the probability itself. Okay, so here we see that the rationale of the current rule is the same than what we had earlier. So basically, we want to move parameters in the direction of the gradient. Okay, we'll see it here. Okay, we want to move parameters in the direction of the gradient of action A. So, but provided that this part is positive. Okay, so if the return is greater than the baseline, our threshold, then we're going to move in the direction of the gradient. Whereas if the return is smaller than the gradient, than the threshold, sorry, or the baseline, we're going to move in an opposite direction of the gradient and move parameters theta so that they decrease the probability of selecting action A. Okay, so in this case, we see that we don't always push the probabilities of action A up, provided the return is greater than 0, of course. But here we see that we have our threshold that we have to yet to decide. But for a given threshold, this threshold determines if we push up or down the probability associated with the action we've just selected. So this version of the algorithm is called reinforce with baseline, and it's a more general version of the reinforce algorithm. But if we can see that reinforce with baseline can still obtain reinforce by setting bs is equal to 0 for all s. Okay, so if we set the baseline equal to 0, then this algorithm just falls back on the regular reinforce algorithm. Okay, so that is very nice, very good, but one question remains. This threshold B, how do we select it? How do we decide what's a suitable value of B? So this is what we're going to discuss in upcoming slides. Okay. So here, this is just repeating what I just mentioned earlier, so I won't repeat that. But as we said, which baseline should we use? The ideal case would be to select the baseline B, which would be the optimal value function associated with state S. Okay, why would that be suitable? It's because whenever so if you have a return who's, okay, how to say that? In average, over the long run, if you select the optimal action, let's write that here. You have the return minus the baseline, and let's say the baseline is the value function and the current state. So if AT is the optimal action, if you select AT being the optimal action, in average, this will be equal to 0, because the expected return, if you take the optimal action, should be 0. Okay, provided you also behave optimally subsequently. Conversely, if you take other actions, then systematically, if you take a suboptimal action, then it should decrease. If you take suboptimal actions, this expectation should be smaller than 0, and therefore you should decrease the probability of the various actions. Okay, so we see that the value function is a meaningful threshold, because if you have the optimal action, so if you select the optimal action, you won't alter probabilities often, whereas if you select suboptimal action, you will drastically reduce the value of that action. Okay, so this means that when your algorithm has kind of narrowed down on more optimal actions, it will be more stable and you won't have very large movements. So once you select the optimal action often, then you will continue select that optimal action often. But for early stages where you're not very sure yet what's the optimal action, you will systematically push down by a lot probabilities associated with suboptimal actions. Okay, so we see that having this state value function as the baseline would be ideal because it would increase the stability of the algorithm, where when you don't know about the optimal action, you adjust your actions a lot, but when you have a good idea about what's your optimal action and you select it often, then you don't move anymore a lot your probability. So this becomes more stable, you have less variability, so the value function would make sense as a baseline. Okay, so that makes sense, but unfortunately, of course, we don't know the optimal value function. If we did, we would have already the optimal policy, so we wouldn't need to go through all these techniques. Okay, so in reinforcement learning, techniques are often meant to calculate the value function because we don't know it in advance. Okay, so we cannot use the baseline as being exactly the value function, but what we could do instead is form estimates of the value function. How to form estimates of the value function? Well, we spend various chapters discussing this. So we can incorporate everything we had earlier. Incorporate everything we had earlier and still form estimates of the value function and use these estimates to incorporate in our algorithm by replacing the baseline by our estimate of the value function. Let me just check the sound. Can I see the sound? I don't see it. Okay, that's fine. Okay, so I'll presume the sound still works well. Okay. Okay, I've skipped the slide. Okay, so now we're here. So what we could do instead is apply the reinforce with baseline. So this is reinforced with baseline. And for the baseline, we can use an approximate value of the value function in the state st. And then this approximate value function, it can be formed exactly like we did in previous chapters, for example in chapter 9. So we can use a semi-gradient approach, for example, to determine to estimate the value function. So we can have a parametric representation or approximation of the value function, and we can try to estimate such parameters. So the textbook proposes the following algorithm as a modified version of the reinforce with baseline, where we have two sets of parameters, theta, which are the parameters driving the policy, and w, which are the parameters driving estimates of the value function. And then our Monte Carlo algorithm would entail refining both parameters on every stage. Okay, so every time we end an episode, we can go through all the time steps and do an update of both. So we can first update the parameters theta driving the policy through this reinforced with baseline approximation, where we use the baseline as the current estimate of the value function. And then we could, on the same step, refine the parameter estimates with, this is the semi-gradient algorithm seen in chapter 9. Okay, so we can see that in this algorithm we have two estimates, one estimate of the policy, one estimate of the value function, and on each step we refine both sets of parameters to improve on our policy and improve on our estimate of the value function. Okay, but this is still again a Monte Carlo algorithm because we have this GT here, which is the return for the entire episode. So we can only apply these updates at the end of the episode. Okay. So are we forced to use a Monte Carlo type of algorithm? Well, the answer is no. So clearly, we could replace the return by like, let's say, truncated returns or other types of targets we've considered in other chapters. So we could consider temporal difference versions of the target. So for example, we can consider GT t plus n instead of GT, which is the sum of the n next rewards plus, so recall there's no discount factor here because we assume we only tackled undiscounted episodic tasks here in this chapter. So the sum of the next n discounted rewards, undiscounted rewards, plus an indicator here, which is the bootstrapping term, which approximates the value function in each step, and this term represents the expected value of all rewards subsequent to time t plus n. Okay, so if we don't want to use a Monte Carlo algorithm and we don't want to wait until the end of the episode to make our updates, then what we can do is simply to replace GT by other targets. Here, we say targets. So for example, the end step TD target could be used here. Okay. So if we do that, then the previous algorithm becomes this. So this is, again, the policy gradient update, kind of the reinforcement with baseline update of the parameters driving the policy here. And here we, on every time step, will also update the parameters driving the estimate of the value function, but here we can replace the GT by the TD end step target. Okay, so why would we do that? Well, it's because it allows us learning quicker. We don't have to wait until the end of the episodes to make these updates. We only have to wait for end steps before making the update instead of the end of the episode. Furthermore, as we mentioned, when we have temporal difference targets instead of Monte Carlo targets, these targets have lower variability, so this might provide less unstable learning and eventually allow learning faster. But the adverse effect of replacing GT by these n-step targets is higher bias because, once again, to approximate the value of all rewards after time t plus n, we use bootstrapping. So we use the estimate of the value function in n steps. And this estimate, it's an estimate, it's not the true value. So there's an error on it. And this will entail that these n-step targets are biased. So we can see that replacing the Monte Carlo target by the n-step target, it has similar effects to what we've discussed earlier. So you have quicker learning with smaller variance, but you have more biased learning. So because of that, it's often advisable in practice to find a suitable trade-off between variance and bias, which is obtained by selecting the suitable parameter n. Okay, so very small n, small variance, large bias, very large n, large variance, small bias. So finding the proper n would be the key here. And here, this previous reinforce version of the reinforce algorithm, where we use bootstrapping, so where we use a TD target instead of a Monte Carlo target, this is referred to as an actor-critic method. Okay, so why do we use the word actor and the word critic here? Critic refers to the fact that the bootstrapping term here is used to judge the value of all subsequent rewards after time t plus n. Okay, so it's a critic because it's not the exact value of these returns, but it's an assessment made by your algorithm based on its current parameter values. Okay, so same as a critic doesn't have the absolute truth, but it uses the information it currently has to assess the value of your action. Okay, so this is because when we use that bootstrapping term here within a TD target, there's a form of critic that is applied to assess the value of your action. The word actor makes reference to the learned policy. Okay, so it's because in a play there's an actor playing a scene, for example, and then there's the critic commenting. Okay, so here it's the same thing. We're learning a policy, and your agent applies the policy it's learning, so it's playing a scene, and then there's the critic, which determines how good were the results, how good was the return, and based on that critic, then we can update the parameters. Okay, so if we go back one slide, here what happens is in practice the agent selects an action, so acts, it's the actor. Based on the action, there's a target that is obtained, but that target is not if in the TD framework, it's not the true rewards you've obtained, but because there's a bootstrapping term, there's a critic being made by your own algorithm. Okay, and this critic comes from the fact that this bootstrapping term here depends on your current parameters, so it's a critic made by your own algorithm. Okay, and based on this critic, then you can calculate this term here and determine if you're going to increase or decrease the probability of your action A. Okay, so this is the intuition about why we use the word actor-critic method to refer to these types of algorithms, where we have both. We are both learning the policy, so this is the actor part, but at the same time we're also learning the value function inexactly, but we are learning it, and this estimated value function acts as a critic to provide information if an action seems good or not. Okay, and one last detail here. throughout this chapter, we use summations over actions because we assume that the action space was finite, okay, or maybe countable, okay. So in practice, you have many Markov decision problems where the action space is infinite, or you have a continuous spectrum of actions. Okay, so if you have a problem like that, instead of having a summation over actions, you would have, for example, an integral over actions, and then the policy, you wouldn't have mass points on each actions, but you would instead have some density over the various actions. Okay, so all these algorithms, they can be adapted to such case. So for example, the policy, instead of being probabilities for each action, you could take a continuous distribution. So here what's proposed by the textbook is it can be a Gaussian distribution over the various actions if actions range between minus infinity or infinity, for example, where you have for this Gaussian distribution, you should specify an average action, an average for the action and a standard deviation, and these average and standard deviation could in turn, of course, depend on the state, because for various states you should have a different action distribution, but also on these parameters, because your adjusting parameters would impact your action distribution and determine what actions you should take more often. So this completes the chapter. It completes the course. So it's been a pleasure to teach you. It's the first time that I do an entire course outline. So I've enjoyed the experience. I hope you did too. And feel free to provide me any feedback about this course so I can continue improving it in the future. Thanks a lot. Have a nice day, and I hope you enjoyed the course.